A very good afternoon to everyone present here. My name is Saurabh, and I'll be taking today's session for Astronomy Code Camp, the third day of the Code Camp. And today we'll be doing some advanced exercise in pulsar astronomy. So, for the first 2 days, and the first day we looked at some basic stuff related to radio astronomy and some basics of Python, which actually helps us, doing all the things that we are going to do today. And it also encapsulates all the basic stuff which you need to do coding in general, and also doing some astronomy related coding as well. So just a second. All right. Okay. So maybe I'll just give it a minute or to see if there is anyone else who will be adding to this camp live stream, and then we'll be starting with the third day of the camp. And for today's camp, what we are going to do is we have some radio astronomical data sets, which is of a pulsar. So, so basically, pulsar is nothing but a collapsed star, which is a neutron star, the end stage of a star, and that neutron star is a very dense object, and that star actually spins at a very high rate, and there are some uh, beams which are ejecting from two different poles of those star, and then it starts spinning, and it starts spinning like a lighthouse. So it's also called the lighthouse in terms of astronomy. So we are going to look at some data sets of a pulsar, of a special kind of pulsar, which is a Vela pulsar. And the data was taken a while back from the UT radio telescope. And today we are going to look at its basic data sets and see how we can actually analyze that data using all the things that we have done in the first and in the second day as well. So in the first day we did all about the plotting and importing libraries and how to deal with different data types. In the second day, which was yesterday, Professor Niraj took the session, and he basically covered all the basics which we are going to need today, which is the Fourier transform. So Fourier transform is sort of a backbone in astronomy, as we can say, because in most of the uh, different fields in physics and astrophysics and cosmology, we need Fourier transform to basically analyze our data in a different domain. So if you have attended yesterday's session, if you haven't attended, you can look at the live stream, which was recorded and uploaded at the same time on YouTube, for going into depth of what a Fourier transform is. But taking it as a clue that maybe most of you guys will be seeing this live stream maybe right now or even afterwards. So what a Fourier transform is, basically converts from one domain to another domain. Now, what exactly do I mean in transferring from one domain is basically, let's say I have some data sets in a time series, right? So let's say, for example, I have a telescope which is pointed at a part of a sky, right? And somewhere there's a pulsar which is rapidly spinning, right? So when we are having some data sets, when we have electromagnetic fields generated from that particular source, and we are basically recovering them uh, through radio telescopes. In our case, which was UT radio telescope, we have those visibilities, we have those data sets in time. So at different time intervals, we recorded data sets. And what we will do today is we analyze those data sets in terms of frequency. So we convert our time series data into a frequency domain. So that's how we are going to look at the data sets. So without any further ado, let's begin today's session. So just give me a second. I'll just quickly share my screen. All right. Okay. So I'm sure that you guys are seeing this particular Jupyter notebook. So for those who does not have any, these data sets, I mean, we are going to use some special data sets. So what you can do is you can go to a particular link on GitHub. So what you have to do is you have to go to github.com/ska.outreach. Um, yeah, right here. So what you have to do is you have to go to this particular link where I've created a repository, and you can simply go to this particular link, and here you can actually download the data sets, which is quite available here. And we are going to use these data sets, and these are uh, time series data sets of radio pulsar, which is Vela pulsar. And here I have also put up some basic introduction and basic methods for installing Python and how to basically install it in different systems. So here you can have a look at as well. So you just have to go to this notebook, and I have pre-installed and pre-made this ready-made notebook in which I've done all the basic analysis and did all the basic stuff which needs to be done for today's session. All right. So here you can see that this. So first, I'll explain that what exactly is this data set of. So we have this data set. We have a sample of the voltage signal, which was obtained from the observation of a Vela pulsar, and this is its astronomical source name with the UT radio telescope. Right. So this OT radio telescope is basically a cylindrical parabola reflecting surface, which has this dimension which is 530-meter long and 30-meter wide. Right, and it is actually inclined in the north-south direction. So here there's some basic details about the type of telescope from which this observation was made, and this observation was conducted at 326.5 megahertz with a bandwidth of 16 megahertz, with a bandwidth of 16.5 megahertz. Right. So the central frequency that at which this was operated was 326 megahertz, which is a low frequency regime, and the bandwidth of this was 16.5 megahertz. And this was actually the voltage signals. Basically, what we have were generated from both north and southern half of the telescope. So in the first half of the today's series, what we're going to do is we're first going to look at some statistical characteristics of any data set or any random distribution that we have in terms of any distribution or data sets that we have. So in yesterday's session, Niraj explained about Gaussian distributions, and he also explained some random processes happening, some basic Gaussian distribution, and doing some basic Fourier transform. So we are going to look at it from an application point of view. So we are going to apply all these things into this domain, into radio astronomy, and going to look how a specific data set should behave in a certain way, and those expectations from those data sets are quite necessary, because if it is not following a certain pattern or certain characteristics like the voltage characteristics, or following this central limit theorem, this might say that maybe this data set is actually biased in some form, maybe some human error or maybe some telescopic error. Right. So it's very important that these data sets should follow some basic structures. So first we are going to need some important libraries. So as from the first two sessions, it was quite evident that we cannot create each and every function, right? So what we need to understand is there are some pre-built libraries by professionals, and these are very sophisticated libraries in which certain algorithms and certain numerical techniques, as we say, are implemented in a very sophisticated, in a very best way as possible. So what we're going to do is we are going to learn about some new libraries as well. So for today's work, we are going to use Matplotlib Library, which is for plotting module, which we used even yesterday and day before yesterday. Next, we are going to use a NumPy library, which is basically used for numerical computations, doing some basic numerical things. And we are going to need another library which is very important for understanding different type of data structures and how and basically structuring the data sets which you have. So for that we are going to use a library called pandas. So it's all right if you do not understand everything at first, but we are just going to have a look at it in a very very simple way, as simple as possible. And finally, we are going to use SciPy. So SciPy is the scientific library which I guess was even used yesterday, which implements most of the numerical things that we know, be it integration, be it differentiation, or taking a derivative, or doing some solving some differential equations, be it of any order, and doing basic Fourier transform, as we said. And also a very important numerical technique we are going to employ today is called curve fitting. So this curve fitting is quite important in terms of understanding a model. So whenever we have some, let's say, so in terms of scientists, when we say that we have some theory about some particular astronomical or any particular physical phenomena, so the first step is basically generating a model, right? So when we generate a model, and then when we have some let's say we have some astronomical source or some astrophysical phenomena, and when we receive the data set, so we try to see how better our model explains that particular astrophysical phenomena. So one method, and one prominent method to do that, is to actually fit our simulation in terms of our modeling with the data sets that we have received. So whenever you try to uh, test your theories, test your modeling techniques, it's always important that your model fits that particular thing. If it does not fit in a good way, then obviously your model will be disregarded. But if your model fits in a good way, then that means that that thing is able to explain that particular phenomenon. So for this we are going to use curve fit, and that is one of the functions of SciPy. Although we are not going to dwell into the numerical algorithm as to how it implements, which is linear regressions and doing some least square methods and all that stuff. We are not going to dwell in with that. Maybe we can take up it as an advanced session in the next camp. So for today, what we are going to do is we are going to use SciPy for doing that particular curve fit, and doing some basic signal processing as we progress on, and then we are going to look at it, the data sets, as to how it appears. Right. So the first step is basically to import all the necessary libraries, right? So here you see that I have implemented some basic libraries, which is Matplotlib and NumPy and SciPy, and then we use some library which is the IPython, which is just for displaying the LaTeX, some LaTeX features. So LaTeX is nothing but a typesetting formatting of of mathematical equations and scientific formulas. So it's not important to use that, but it makes things look very much in a good way. It presents our work in a very good way. So we're going to use that. So our first step in doing this is first importing our data sets, right? So for that, we basically use pandas library, and there is a function in that particular library called read_table. So as you see that I have imported this library as PD. So we have to take care of that particular norm that we have used, the particular convention for importing that library, as told in previous sessions, that we can name it as per whatever you like. So right now I'm using NumPy as NP, I'm using pandas library as PD, and matplotlib.pyplot as PLT, scipy.optimize. I have imported certain functions from that. I haven't imported the whole library. And yeah, so we are going to use these functions directly. Right. So the first is importing this data set. So for this, we use this read_table. So this function is quite so first let's just run this data set and see. Right. Okay. So this read_table is a very important function. It basically reads in the data set whatever you have in let's say in a format of a table. Right. So if you want to understand more about this particular function, what you could do is you can simply type in this command and use the help menu to understand it more about this particular function. Right. So here you can see that what it does is it takes lots and lots of arguments. Although these all are quite optional. The main one is the file path in which your file this particular data set is stored. So I urge you to first download the data set, whatever you have from this particular website, right? And you have to use the website and download a dataset from, or download any each of these files, which is around 250 MBs or something like that. So for that, first you need to download this file. Let's say I have clicked on this particular file, which starts with this. And I just need to download it, and then it will just download it in the background itself. Right. So this is how we are going to do these things. It's around 200 MBs, so we don't need to worry about this. And so we have multiple data sets which are 1 second each apart, and we have to simply just use any of those files and work on with that particular data set. All right. So here we have pandas read underscore table function that we are going to use for reading the data set, and we have this data sets. Just the first argument is basically the file path, that where exactly your file is located. It can be anywhere. So in my for example, in my system, it's basically in this particular folder. So I have to input the whole folder name. Then, and it should be in the inverted quotes, as I mentioned that strings are always written in inverted inverted commas, so you have to use that. Then you have this another argument that is important, and it actually differs from datasets to datasets. So this delimiter, so the delimiter is nothing but the separation, how the separation of columns are, right, in the dataset. So first you need to understand that what type of datasets you are dealing with, and how exactly the column by column is how's the separation column by column, right? So here we see that the column is actually separated by a simple space. So that's why I'm using the delimiter equals to inverted commas with a space of with a blank space, right? So that means that the columns is separated by space. And as it's mentioned that header equals to none. So header, so every file, mostly every file has this thing called header. So header is nothing but a part of the data set which tells you more about that what exactly is that data set contains. It's not exactly a part of that data, but it contains the information which you might require to understand this thing, right? Sorry about this. All right. So it's important that sometimes that you read some files for this particular thing. So yeah. Now what we need to do is we input. Apologies, I think there's some issue. Yeah, I need to just turn this thing out. I think there's some issue. Just a second. Apologies for this. Oh, so sorry about this interruption. Suddenly, I think that maybe there was some issue. I'll just try to stream it again. All right. So we are talking about this particular function, which is the header file. So normally what happens that in a file, in any file, mostly if you see some images file, which is the FITS format, flexible image transport format. So in this, there is some header files which tells you what type of file it is. It can be the name of the source. It can be what frequency it was operated at, or what was the bandwidth, or details about the particular image, frequent and like the resolution, and all the basic stuff which is required about the basic information about the data set. So here we have already removed that information because we are not in need of that. We have already supplied the basic data set which needs to be known in this format here. So the data set is none. So header, if there is no header, so we have set header equals to none, right? And then we run this particular format. So now when we have this df file, what we can do is we can simply assign a particular variable to this df, and then simply use our we converted this whole table into an array table, right? Because sometimes it's easier to uh, basically think of everything as arrays and deal with this particular format of numpy arrays, because it becomes it easier for the computations to work out, right? Element by element multiplication and doing some basic matrix multiplication. So it becomes easier if we convert that format into a simple numpy arrays, right? So here what we did is we did nothing. We just simply converted this whole table into a numpy array using this definition, which is np dot as array. All right. So that's how we did it. Right. So let's say if I am able to. So we're just running this code, and it might take a while to actually read this whole file because it contains a lot of columns. So here what we did is we first read the file with df function, then we with this assigned the time, the table format into this df variable, then we converted it into a number array in the data format. So if you see that, first we see how this table looks like. So you can simply just put the df command in which the table was stored, and it shows something like this. Right. So what it's showing is that there are total number of 2 columns, right? This is the first column. This is the second column. Right? Numbers start from 0, and this is the left side. This particular is showing this particular serial number to this particular. So these are the data sets. -65, -5. So the first column represents the data set from the north pole of the radio telescope, and this second column represents the south column, the south pole of that telescope, right? So the first column is the data sets, and this is it. And you can see that the total of is around 3071 times night, around somewhere around, if I'm not wrong, 30 million or something like that. This is how many rows and columns are there, right? And if we see that how its data, how the arrays look like, then it looks like something this, which is something which is easier to interpret in terms of Python and computation. So if you see that, so here what we are doing is, so first we are choosing just 512 samples, so as to look at how it is following the normal characteristics. So if you have done some basic statistics, if you have understand some basic statistics and also did some calculus, maybe you would have come out with this particular term, which is a central limit theorem. So it basically suggests that basically any distribution, any random distribution of data set which we have, it should follow a Gaussian distribution. A Gaussian distribution is sort of like a bell-like curve, something like this, right? So there's sort of a peak and something like that. So in these COVID times, we are very much familiar as to how curve sort of looks like. So this is like the sort of like that itself. So there is a peak which represents that what is the mean value of that particular whole data set. So any random distribution or any random data set should follow this. So we are just trying to understand how to if this data set actually looks like that or not. So for this, what we are doing is we are trying to select 512 samples from the north pole of the data set and 512 samples from second pole, the south pole of the data set, right? So for this, what we are doing is first we create an empty list. So empty list is something like which you can think in like as in high school you have this empty set, right? When we study these basic abstract mathematics, so sets and theories and all sort of things. So we have this empty set in which I can input as anything into that, right? So here I'm creating an empty list in which I can input anything. And so what I'm doing, I'm running a loop for in this with this particular with this particular table structure. So what I'm doing is I'm running a loop for I in range n max. So range is another function which is an inbuilt function. What it does is that the number that I input inside range, let's say 10, it generates a list of values from 0 to 10. So here it's representing 0 to 10. Right? You can do the same thing with print, and it would just give the same thing. What it does is it's creating a total number of numbers between that particular value and 0. So let's say it's saying 0 to 10, which means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Not counting the last number. That is how it works. So it goes on with a similar thing. The nmax is 512. So it creates number from 0 to 511, which is 512 numbers itself, right? So this is what it's doing. So for I in range nmax, which is 512 numbers, so each and every number will be assigned one serial number. So this is what it's doing, is that I is 0. So first it's doing it iterates from from the starting value, from the beginning value to the end value. So the first is 0, right, for I in nmax. So first I is 0. So for what it's doing is that, maybe I have skipped a step. Let's say the north pole values, I'm associating north pole values as npv. Okay, I'm associating a value. So df dot values. So I'm using this data set, this this table structure, because it makes it easier to store values for now. And I can do it like this: df dot values. This dot values, what it does is it extracts the values from this structure, right? So when I do this thing, when I this square bracket, it means that I am trying to extract the values and at what serial number, right? So let's say if I have 10 numbers, okay, let me do this. So let's say I create a list of 10 numbers. Let's say 0, 1, 3, 4. Okay, let's say I'm creating a list of 5 numbers, right? Like this. Now I want to extract the second value of this particular variable. So what I can do is I can simply write 1. So as I told you that the second value will be represented by 1 as the counting starts from 0. So let's name it another number. Okay. Something like this. Yeah. So let's say I'm extracting the second number. So I will just do square bracket, which is sort of slicing thing. And I do this like this, and it gives me the value which is at the second position, which is 323. Now, if I want, at a position, let's say 494. So, sorry, I mean, it is third value. You give me this 494. So this is at the 4th place, and n minus 1 represents that particular number in that particular series. The last number is 4th one, which will give me this. And if I increase the number, it will show an error. It says list index out of range, which means the index that I'm using here, it no longer, it does not exist, in the frame of this particular list. And as you know that there are a total number of 5 numbers, and now I want a 6th value. So obviously it's exceeding this particular limit, right? So we won't be having that. We will be facing an issue. So this is what's being done here. So what I'm doing is I'm trying to extract those values, right? So df. So now here what I'm doing is I'm having 2 things, right? And these 2 things, why? Because it is a 2D column. I have 2 columns of data sets, right? One is the north part and one is the south part. So if I do this thing, let's say I just click df dot values, right? I do this, it gives me the array of values. So I think there was no need of using this thing, right? So delimiter values, what it does is create the array of values, numpy array, and when I do this thing 0, it gives me the 0th row. Right? This gives me the 0th row. So it gives me 65 and minus 4. All right. But when I do, I want the first column value, which is the north part. I will take it as a, so north part is the first column. This is the second column. So you can think it as a sort of a matrix, right? So if you want to extract, 0th column and first row value, so I can do it like this. So it's the 0th row. This is the first row, and this is the first column, right? So this is how it will give me the value 65. Right, and if I do this one, it gives me the second column value. Now if I do third, if I do 2, which means third column, so I do not have any column, so that's why it says that index is bound for axis 0 with size 2. The size is 2, which means there are 2 columns. So for this, I just, so the second thing has to be switched from 0 or 1. 0 represents the first column, 1 represents the second column. Meanwhile, this thing, this number in the first thing, it is the number of rows. So if you see here, there are so many rows, right? So if you want to know the rows, what you can do is you can, do this whole thing, and you can write dot shape, which tell me that what is exactly the shape, or in terms of matrix, you can think it of as what is the order of that matrix, right? It's a 2 cross 2 matrix or something like that. So here it is like this. So it's something like the number of rows are this, number of columns is 2, right? So this is how it's going on. So the first this first bracket can run from 0 to this. Meanwhile, the second one needs to run from 0 and 1 only, right? So for this thing, 0 represents north pole, 1 represents south pole. So I'm using this thing. Now this is 0th column, this is first column. Now the first has to go on from this is from 0 to this particular 3 million or something like this. But I just want 512 values. This means that this thing needs to be changed every time. It needs to iterate. Like first it has to go 0, then 1, then 2, then 511, right? And for this I'm using this loop. So this I value is changing every time. So this is NPV. Similarly, what I can do is, so let's say I have, now we have south pole values, which is SPV. Let's say we can do that like this, right? Which gives me south pole values. Now, what I want to do is every time it takes out a value, every time it takes out one single value, it should put into that empty list which I created here, right? So whenever we want to insert an element, which we call this as an element, right, in a list. Whenever I want to insert an element into an empty list, I will use the command which is called append, right? So that empty list dot append, which means I'm appending my value in this particular list. So that particular list should go in with this particular value, which is NPV. And similarly, for the south pole, it will be SPV. And this ran very smoothly, I suppose. And okay. So here I can see that what my value contains. So I can simply, now this list is no longer empty. It is v underscore nth, and you can see now it would contain 511 samples. How I can know that it contains those many samples? So for list, you cannot use that shape function because it does not have any shape, as only numpy arrays will have that shape function, right? Only numpy arrays can have that particular thing. For list, what you can do is, to understand the list, you can do simply put the len command, which is for length, and put this v underscore np, and you'll see that it contains 512 values, right? So it contains 512 values. And similarly, if you want to check what is the number of values in s and th, it also contains, it's okay, it's v underscore sh. It also contains 512 values in a similar way. All right. So at this point, I'll first need to see if there are any questions, and then maybe I can move on. If there are any questions. All right, right now I do not see
something like this, but I just want 5.
So maybe I think I can move on right now.
Maybe I think I can.
Screen of a PC too small for clearly visible. Okay, I just saw those comments. Please increase the screen size. Oh, apologies. I was using small size. Okay. All right. All right. I hope now it's clearly visible. All right. So I don't see any questions which are related to this right now. So right now what we did is we appended the first column libraries, the first column into an empty list and second column into another list. Now those are no longer empty, as we say, and they contain 512 samples of the data sets, right? So now what I need to understand, I need to see that what is the mean and standard deviation of that data set, right? Because so this means that I need to sort of normalize my data set. Every data set which you see should have some mean, what is the average value of this thing and what is the standard deviation from this particular mean value. Now for the North Pole data set, what I can do is I can simply fit. I can use a SciPy function called norm. What it does is it fits my data set to a Gaussian function and print out the values. So what is this is there's a function called norm and there's this module called norm and there's a function called fit, right? It's a norm dot fit. So it returns the MLE values, which is maximum likelihood estimate. You need to worry about that for now. So for the data sets, so it fits that. All right. So there's this thing. So even if you do not need to use this norm, what you can do is you can also use mean of this function of numpy, and it will give you the same or very similar answer, which is around 3.55. So so here what we are doing is this non.fit, it actually exports two parameters and return two values, which is the mean and standard deviation. So mu1 comma sec2, I can assign those two return values to these two variables from the North Pole dataset. And similarly, I use mu2 and sec2 from the South Pole dataset, right? So here I have mu1, mu2, and sec1 and sec2. So I'm now printing the values using this simple function. So I'm using the print function to see what exactly are the values. So here I have mean1, which is represented by mu1. Then I have std1, which is sigma standard, which is standard deviation 1. Similarly for mu2 sigma 2. So you see that the mean value of the first function is around 3.455, and standard deviation from the North Pole is somewhere around this. Meanwhile, the South Pole data set is somewhat around zero point 0.3, which is much different from this, and similarly, which is 30.66, which is quite understandable because from North side data set there might be some issues with the how it's taking the data sets. Meanwhile, the South Pole data sets is also taking their own sort of thing, so there might be different noises which might make this happen. If this would similar, then that would have pointed out to a issue that maybe they have some correlation, but right now they should be uncorrelated. They shouldn't be correlated. So this is what we have right now. So now what we need to see, we need to see the histogram of these data sets, which means basic distribution, how these distribution things. So for this I'm using simple histogram, which is a hist function of this matplotlib, which is plt.hist, which plots an histogram simply. And for this I have I just need to supply the data sets which I have. So for this, I create a subplot. There's a lot of ways in which I can do that. Either I can create plt.subplot and tell me how many columns and how many rows and how many figures there are totally, and then simply use this plotting function. Or I can use adding subplot, which we use in the first thing. Right. So anyway, it seems all right. So for this, I'm first seeing the histogram from the North Pole and histogram for the South Pole. Now here, when you see the histogram, it clearly explains that we are seeing a Gaussian distribution, and this is what was actually needed, right? Because we needed to see that what sort of distribution it follows, and then explained from the central limit theorem, the random distribution should follow a Gaussian distribution. Hence, we are right now seeing 512 numbers of these samples. Now it's totally up to us if I want to see more number of samples. So what I can do is I can simply multiply it by 2 and see which is 101,024 samples, and it would give me something like this. Much steeper um, much steeper plots, right? But for now, let's keep it to 512 samples. All right. So now we have this. Okay. Right. So this was the first part of the function, which is plotting and seeing the basic characteristics of a random distribution function, which is Gaussian distribution, which it should follow. And right now we are saying that yes, it follows. Right now, what we need to see is how well it actually follows the Gaussian distribution. So this means that we need to fit a Gaussian curve to this, Gaussian curve to the data set which we have received right now. So for this, what I'm using is I'm using a function called norm.pdf, which is a one distribution function. And so what I'm doing is I'm using this PDF. What it does is it creates a probability density function of a data set which we have right now. And in our case, it is Gaussian distribution function, which it should follow. And this is what we're seeing right now. So from the histogram, when we first make an histogram, these are the values which we return, which is number of values, then bins, and then patches. No need to understand this right now. Maybe we can proceed it further because this comes into some advanced sections, right? And because we need these values to basically create the density function, the probability density, that what exactly it is following right now. Right. So for this, I'm using the bins and what exactly is the mean and standard deviation of that function. All right. So either you can create your own, Gaussian function, as I mentioned, that you can use def and create your own function. So you can create a Gaussian function which has, certain parameters which normally a Gaussian distribution has, which is x, then standard deviation or the mean, then sigma, which is standard deviation, and so on, so on. Right. So for 1D distribution of this Gaussian distribution function, we have mu and sigma. For 2D distribution, we have two means and two standard deviation. So it's totally up to us how you want to use it. So right now, we are using one-dimensional distribution. Right, and this is how we see it. Right. So we create a distribution function which is the best fit of this, and we see how it is following. I guess they did something wrong. We run it again. All right. Now the histograms. Okay, maybe there is some issue. Okay. Seems right now it's not following what it should follow. Maybe some issue with the updating my library right now. Okay, okay. So let's just see. This one. Maybe I'm missing something. All right, I guess it seems there's this an issue with the updating of my library. I'm not able to see that particular function. So in simple terms, right now it seems not working. But what we are trying to do here is we are trying to see how better it is actually trying to fit a Gaussian function, which seems it's not working at the moment. But yeah, this is our understanding. So what we do is we try to fit the data and see how well a Gaussian distribution actually works. So maybe here it was still there, I guess. And I'll show how this looks like. Okay. Yeah. So this is what it's supposed to look like. So what we're doing is we have this our probability density function, which is here Gaussian distribution function, and we see how beautifully it fits our data set. Right. This is for the North Pole data set, and this is for the South Pole fit. Right. So this is actually for the voltage distribution. So right now what we have the voltages, right? The voltages from North Pole and the South Pole. These are actually converted from the electromagnetic field vectors, the electromagnetic field radiation which we receive at the radio telescopes, and it has been pre-analyzed and selected for this particular analysis, which is the statistical analysis of our analysis. So this was a basic Gaussian distribution function and how to fit a function with our data set. So you can use this as a template as well. And whenever you have some data set, you can try to follow this trend and see what are the different uh, characteristics of that radioastronomical data or any physical phenomena data set you have, and what it follows and how better it follows the data set. If there is any correlation between different structures of your data, or maybe if there is also standard deviation, what's the mean of that data set, which can help you better understand about what trend it should follow. Right. So now what we are doing, so after doing this, the main thing is to understand about the power. Right. So power in terms of in our analysis, what power is basically the square of the magnitude of the complex, not the complex, but the voltages, right? So it's basically the square of the magnitude of the uh, voltages. So here what we are doing is we're doing nothing. We are just squaring our you know voltage to get the power of our data set, which is, and then we convert it into a simple list. Then similarly we did for the south pole and for the north pole, and now we are trying to see how it follows. So it actually follows a an exponential function, which is if you go into studying them more, if you study more, you'll understand that it will actually follow exponential function, and it no longer follows this Gaussian fit, right? When you square it, so you can simply you can even do this thing by squaring a Gaussian function, and you can see for yourself how it actually happens, right? So we see that it's actually following a exponential function. So this was the main exercise of the first half of this study of understanding this basic thing, which is understanding power spectrum. Sorry, which is understanding the basic behavior of voltage and understanding how actually power actually looks like in terms of voltages. And this is just all statistical analysis right now. This is just there is no any weightage of these things in terms of putting into concrete something, but this is just for our own satisfaction and for our own knowledge, for our own information, that whether the data I am receiving it is actually good or not, to test our modeling and to test the hypothesis in terms of what we when we say. So in statistical analysis, if you study, where you understand what are the different statistical methods to process the data, to analyze it, and to test your own model, is hypothesis testing. So in hypothesis testing, what happens is either your hypothesis is true or not. So our hypothesis is basically the model which I have. I check what is the probability that my model is actually true, right? So right now in terms of statistical analysis, what we do is in the first term, in the first hypothesis that we study is called the null hypothesis. So null hypothesis states that the model that I have, the probability of the model that I have is very low, right? So this means that I'm actually proposing it in an opposite way. So null hypothesis suggests it is basically to find out what is the probability that my model that I have does not explain the current observations, right? So if the probability is very high that my model does not explain that particular observation or particular astrophysical phenomena, that means my modeling is not correct, right? And then we search for this particular p value that we have, and then go on for all those z factor and all, find all those things in using statistical methods, right? So this first thing is testing our hypothesis, and if the probability value is lower than a certain value, which is around 0.05, then we say with strong evidence, with strong confidence, in terms of confidence we mean scientific confidence, that basically our model is actually correct, and there is some data present which is following my own modeling, right? And the alternate hypothesis is which supports our model, right? That is the alternate hypothesis. So null hypothesis states that my model is not supporting the current observations. Alternate is quite the opposite, that my model is supporting this. So we test our we test this thing, we do analysis in favor of null hypothesis, as to remove any sort of bias in our own calculations, in our numerical computations, and then we check that what's the probability that my model does not work. If the probability is very low, this suggests a sort of favor in the model of which I have developed for understanding that phenomenon, right? So this is actually all part of a big thing, which is statistical analysis, and it's quite important to do this thing, because sometimes you have some correlations in your data sets which would suggest that someone has biased, has some bias in the data set. Someone has what we say is has tempered with the data set, right? Which is actually not ethically right, or even sometimes it might be some human mistakes, or even some some other errors or noises that might turn out this thing. So this is the first thing. Right. So at this point, I'd like to take a stop maybe for a minute or two and see if there are any questions that I need to take up. Okay, I see no questions as of now. All right. Okay. Yeah. So I see that there are no questions. Maybe we can just move on. So I just need to check one thing. Hmm. I know that was just a break of a minute, and this is for the audience maybe who will see that afterwards as well. So what we're going to do is right now is we're trying to see how better it to look at the power spectrum, right? So power spectrum is quite an interesting topic, and I think maybe we'll skip this thing and just do this basic plotting, to get a better look as to how things look in the frequency domain, right? And which is doing the basic Fourier transform. So in yesterday's session by Niroj, he explained what exactly is a Fourier transform, or maybe he just did how to do Fourier transform, right? So if I can just take a minute maybe just to explain what Fourier transform is. So Fourier transform is nothing but transferring the data set from one domain to the another domain, right? So here there's a basic example. So here what you can see is, first let's see that how the data set is behaving as the time progresses. So, all right, so this is how the data is currently behaving when it's moving into time. So this is a sample of around 500 seconds or something, milliseconds, the data set, and right now we are just taking 512 samples, which represents around 512 milliseconds. And no, not milliseconds, somewhat around nanoseconds, because we're just taking a small part of it, right? But this is how on the x-axis you see it's a time domain, and in the y-axis you see voltages. So this is how the voltage is currently behaving, right, in the time domain. Now let's see how this actually looks like in the frequency domain. So why are we doing this is basically sometimes what happens is that we need to see that how the function behaves, and sometimes we actually miss out things in from one perspective, right? So it's all a matter of perspective. So if you see things like from this way, and you might not see some things which are hidden behind it, so you might look at it from another way, right? And this is actually what we see as a time series data set, right? So from, let's say, if there's a sine wave which is going like this, so the sine wave is actually a moving in one domain, right? And I'm not seeing something which might be behind that. So if I simply, let's say this is the sine wave, and if I simply rotate it from one perspective, What I'll see things, I'll just see that there's something going up and down, up and down. All right. So but it is actually moving with only one frequency. Right. So that's when the frequency domain of sine wave, I'll just see one particular point. Right, as what Niraj explained in yesterday's session. So it is all about conversion from one domain to the another domain. Right. So here the time series data is converted into frequency domain data, which means how my signal is changing with respect to different frequencies. As I mentioned, that the frequency, the central frequency at which the rotary ray telescope is working is 326.5 megahertz with a bandwidth of 16.5 megahertz. Right, 16.5 left side, 15.5 right. 16.5 megahertz total. Yeah. So this is how the time series data sets look like. So now we do a quick Fourier transform. Now for doing Fourier transform in computational domain. So if you have studied the theoretical formula, how doing a Fourier transform is basically doing an integration with some particular factor and then the main data set, right? So when we try to do this Fourier transform into computational and we in terms of numerical work, we basically try to do it in discrete way, right, at some discrete values, because integration is over continuous set of values, like right from minus infinity to infinity, from 0 to pi or 0 to 2 pi. So it's a continuous set. But in terms of computation, it does not understand what a computation is, what a continuous function is, or even how continuity actually works, right? You cannot work in real numbers here. Here you have to go and discrete values. So basically that integration thing is actually turned into a sigma, which is averaging, which is basically doing the sum from this particular thing to this particular thing with some discrete sets, right? So for this we have another algorithm which is called fast Fourier transform, right, which is algorithm subset of discrete Fourier transform, which actually does this whole Fourier transform thing, right? So if you want to see how it happens, so we have a Fourier transform package in NumPy, which is np.fft, and then there are different functions which does a different type of function. So if you want to do Fourier transform, which is FFT, which is fast Fourier transform, you can simply just make a question mark, and here it will explain how this one-dimensional discrete Fourier transform works. Right? So the function computes one-dimensional discrete Fourier transform, which is DFT, with efficient fast Fourier transform algorithm. Right? So FFT is the main algorithm, and DFT is the main topic. So FFT is a subset of discrete Fourier transform. Right? So FFT does the first Fourier transform in one domain. Right. So what we did is here. So we basically did. So here you see np.fft. It Fourier transform the voltage of south pole. And okay, let's put it in this way. Right. So all right. So here what we did is first we did the Fourier transform of the north pole, which is v underscore nth, and then we did the first Fourier transform of the south pole, which is vs underscore ffth, and this is explained by v underscore this, and this is the voltages using this function of fft. We simply run this command, and now we plot them, right? The same thing which we did here is the subplots. Either you can subplot it or you can do a simple thing. But let's say if I just do this, lt.plot v underscore nth. This is how the time domain looks like, right? Let's make some title to it as well. Which is time domain. All right, and now we'll do PLT. Let's see how South Pole looks like. But even that's the part of the thing. PLT dot plot, which is v underscore xth. Title, time domain, just for South Pole, and here it is actually for North Pole. Okay. This is what it's South Pole. So you see how they are actually behaving, yet differently, right? So let's see how the time domain, the frequency domain looks like. Plot vn underscore Fft. So basically, this is So let's see. So first, if you see the how the data set is, so it is basically in the complex domain, which is obviously which has to be right. That this is the main point of doing Fourier transform. It gives a complex voltages as well. It gives a complex part. So we actually need to plot the absolute values, so absolute magnitudes. So if you have understood, so if you know what exactly is the absolute value, so I can just simply do apps dot bff nfft, let's say absolute values. Absolute value is it is basically the magnitude, which is the the simple multiplication of the complex into uh, so let's say we have z and z into z bar, which is the complex conjugate. Yes, complex conjugate. So we basically multiply that, and then that's how we get the magnitude, right? But here what we'll do, or let's say the absolute value, but here we can use a very simple function, which is abs. So abs is the inbuilt function of Python as well, which can give the absolute value of this thing. So we just simply need to use this bn underscore 50. So it will give me the absolute value of north pole data. And similarly, if I want south, so 50 equals to absolute of v underscore x underscore 50. It gives me the south pole. Now let's see how it's acting. Okay. Yeah. So here, what we see right now is the Fourier transform of this data set. So this is the south pole. This is so here. So in the time domain, you see that there are different So here, what it's saying that on the left hand side is the frequencies, and this is the this is different frequency. This is the voltages, right? So you can see that how it's scattered over different frequencies, different values of voltages, right? And here it's on the time samples. So this is the power of Fourier transform. You can see that what particular frequency it's actually working on. Right, right now you see that it is on the left hand side, it's on the right hand side, and it's sort of symmetric. So what we need is we just need a first half of that particular function, right? So we can simply use another thing, which is np.fft shift. Right, so Fft Shift, what it does is it basically shifts the whole thing from one domain to it basically shifts this whole thing from 0 to 512. Sometimes it happens that the central frequency is not at the center, but it's at the left hand side. So we need to actually shift this from this thing, right? So we just need only the the first half. So what we can do is you can do something like this. So instead of doing the Fft Shift thing, I can do it here itself while doing this absolute. All right, absolute is should be done at the later stage, right? And same thing should happen here. So right now I just need the first 256 points, because it's actually symmetric on the left, because the frequency is positive and negative. Let's say if you do the sine function, so either the frequency can be 1, let's say if y is equal to sine x, right? The frequency can be 1 or even -1. So it will show the frequency domain 2 bars, right? So which is on the left hand side and right hand side. So that's why we need the only one part of it. So yeah, I guess slicing was done yesterday, so I'm going to skip that part. If you already are aware of how to do the slicing part, so for that you simply need to do this thing. So what I'm doing is I'm taking the data set from 0 to 256 point using a semicolon thing, right? So if you want some particular set, from particular value to another value in terms of index. So here I'm defining the index, right? It is taking from the 0th value, which is the first value, till the 256th value, which in terms is 255. So this is how it's going to be. So this is how this actually behaves, and in terms of frequency, you see that there is actually very low on the one end, and then it goes at peak at some particular thing, and then it comes back. right? This is what we say is Fourier transform in the frequency domain, the data set. And similarly, we can do this thing in terms of south, which is S and square T. And in the south one, it looks actually similar. All right, but we need the first 256 points. We'll do the same thing, and yeah. So here we see that it actually follows a very similar pattern in the frequency domain, right? So this is actually what we needed right now is how exactly is the data set behaving, right? That is the main idea behind doing all these things, right? So this was the first part, and then after that comes the power spectra and doing this whole thing, which is much more complicated as to what we have done till now. And then comes the dynamic spectra, which is the most interesting thing, which is basically right now we are doing voltages versus time, then voltage versus frequency, and then we did power versus frequency and power versus time. Now what we'll do is basically frequency versus time. With time, how the frequency is changing, and every time we have this pulsar flash, in the line of sight, we receive a pulse, and this is how we see that pulse, right? Where we where we do this whole thing, right? This is basically what we need, the dynamic spectra, the whole thing behind this thing. So each and every flash which you see here right now, but this flash indicates that we have a strong signal. But as you see that as the time progresses, the frequency, the frequency is high, right? I mean, the frequency changes. This happens why? I mean, that higher frequency waves reaches us at an earlier time compared to low frequency. So you see, the low frequency are reaching us at a later time. This is actually an astrophysical phenomena called dispersion. So the dispersion means that whenever there is whenever there is some electromagnetic radiation flowing through the plasma or the interstellar medium, right? So whenever it's flowing through the interstellar medium, which contains gases, radiation, all sort of particles, dust, there's some solid material as well, planets and all the other things. What happens is there, due to that plasma, due to that interstellar medium, the higher frequency waves are able to travel faster than I should rather put it like this: the lower frequency waves are traveling slower than those high frequency uh, waves, because higher frequency have a higher energy, hence they are able to travel through that medium very easily compared to low frequency which has low energy, right? So that could be easy to imagine, right? So this is how it happens. So lower frequency waves have lower energy, hence they are actually slowed down with that interstellar media, because they're constantly interacting with that interstellar media, having dispersion, and that's why they're reaching us at a later time. So the another aspect of doing this whole thing is to basically de-disperse this thing, right? We need to basically make these slanting lines straight, which means that for each and every frequency, I have to compensate a particular time delay. I have to introduce a time delay at those high frequency waves, right? And when I do this thing, this is called de-dispersion. And for this, I need different values of de-dispersion, values of the interstellar medium, and all those things. This is the cross correlation. This is how it actually look like. This is what it should look like, right? When we try to de-dispose it, this is actually the data set of a pulsar. And when we find that what is the time interval between those pulses, the consecutive pulses which we see here, this is the time period of a pulsar. So at this, using this particular data set, we can determine that how fast a radio pulsar is rotating. This is how we can determine its periodicity, right? So when we fold this, we can literally fold each and every pulse over one another, we can find a general profile of a pulsar, right? So this is the whole process of doing a basic pulsar analysis using the simple data set which we have. And in that particular data set, we already pre-analyzed and saw that there is some pulsar, signatures of a pulsar, and that's why we are proceeding with this whole analysis. And this is actually the whole main point of this whole analysis. So I think the dynamic spectra and doing all these things might be out of the scope of this whole session. But in today's session, the main important thing was to understand how to import the data set. I know doing some basic statistical analysis of the data set, which is basically simple Gaussian distribution fitting, and seeing if it is following central limit theorem, or if it's following a random distribution error or random distribution curve or not, which we say that it is following by looking at some data sets, at some random samples, then following if how the power looks like, which is basically the square of the magnitude um, of the data set of the voltages that we have, simply squared it, and which should follow an exponential profile. Doing simple mathematical calculation would be quite evident in that situation. And then seeing how it looks like into the time domain, and then into the frequency domain, which is at different frequencies how the data set is behaving, which would tell us more about the interstellar medium, and as well of pulsar as well. So that's the whole thing of of this whole analysis. So this dynamic spectra, and this power spectrum, and this whole d-dispersion and time period, and holding the pulsar or a pulsar profile, it's actually a matter of another day, or maybe of a camp which is advanced enough so to actually carry on with this whole thing. So I think I'm going to stop in here, and if there are any questions, I'm going to take them. And if there are not no questions, and I might as well stop here as well. So for now, what I think is need. All right, so I'm now going to stop my screen and see if there are any questions or not. All right, so I do not see any questions as of now, and maybe for people who will be watching this later on, can simply ask the questions, or can even mail me, and then I'll be happy to take up any questions that might be related to this particular analysis. All right, so thank you very much for joining us, for all the students who joined us today, and then we shall continue this whole thing in an advanced version of this camp. So we'll be looking more into that. So I would like to thank the Nehru Planetarium, Nehru Memorial Museum Library for organizing the Astronomy Code Camp. Hope you guys would have had some fun, or had some understanding, had some learning regarding all this analysis and this whole thing. So it was a great experience. So I'd like to end this broadcast. Thank you.